time this semester, and our guest, our speaker today is Malte Loft, and you all know him from retreats and RTG meetings and so on. He's working on this surface wave model, and he will give us some impressions today, right?
Yes. Thank you all for coming and attending to my talk. Hopefully you can hear me. I think the microphone should work perfectly somehow. The talk will mostly about our model and what we are doing in T4 and why we are doing this. So I would like to give you a basic understanding of what we are doing. And I will start with a small introduction. Also, the second part will be about the modeling itself. And then I will show some, hopefully interesting results. And then I will head up to some future directions. To start with the introduction, basically, the main idea is, or the main issue is that small-scale processes are usually hardly resolved or not at all resolved by ocean models or global simulation models. So there is always a need for modeling or parameterizations. And one main issue is that the energy controlling physics are not yet fully understood. So there is a need for research. And one way to get into the physics or to get new insights in the physics is to use experiments. And I know this is a rough statement, but usually you can measure actual physics with using experiments. Of course, you have measurement errors and biases and measurement noise, but they are usually very fast and well established. And the main disadvantage, at least in this field or in these kind of experiments that I'm looking at, the big disadvantage is that we have often a lack of data. And for this, we can use simulations because usually we have very huge data sets in simulations. They are highly resolved, or they can be highly resolved in space and time. And they are mostly easy to reproduce. But the disadvantage here is that often we have idealized cases that we are looking at. We have some sort of simplification or some simplification of our model that is not as complex as the reality, for example. And our research approach, or basically our project, is divided into different work packages. We have our experiments, which is WP1. This is mostly done by Janina and Mark, and they are focusing on particle image velocimetry. So they are doing some high resolved measurements of the velocity fields close to the surface. They are also able to calculate gradients close to the surface. And this is, the PIV is quite useful to counteract this disadvantage that I mentioned before, so that we can get a lot of data, a lot of velocity vectors close to the surface. And they have done, in the current project period, they have done some experiments in the wind wave tank, and also in nature, so in the Stettiner, which is basically just a big lake next to the Baltic Sea, where they performed these PIV measurements. And here you see one picture. You see the horizontal velocity field close to the surface. So this is a real surface wave in the Stettiner. And one problem here is, as you can notice, now I can test my laser pointer here, my digital laser pointer, and you can see these black areas here, and there they have missing data points, which is basically this is caused by missing particles in the air. So this experiment is based on particles, as the name says. So they are tracking the velocity of particles. And it's very hard to distribute these particles evenly in the air. And that's why we can have sometimes these dark black areas where we are just have missing data. And here we can supplement or support the experiments with simulations. So the idea is to do coupled two-phase flow simulations. We would also like to consider high Reynolds scenarios, so similar waves like in the Baltic Sea. And we would like to have a look at the energy budget and also at different, more complex phenomena like breaking events, for example. And here, just to give you a short impression, we see two instantaneous velocity fields of the horizontal component and the vertical component at the bottom. And this is just a surface wave that is traveling from the right, and yeah, behind the hand. So these two work packages are the so-called foundation of our project, if you say so. And our third work package is the ocean modeling, and the idea is that we supplement, or the WP1 and WP2 support each other, and later on the idea is to generalize some sort of parameterization that can support the ocean modeling and prepare a better to use our knowledge also for more global models, but this is future and not the current work in our project. And now we come to the second part, it's the modeling. First of all, our basic idea is to model the air phase and the water phase simultaneously. So we have one global velocity field, so no explicit interface. And that's a big difference to the classic approach where we define an interface or a prescribed surface. So most often these one-phase simulations, the prescribed surface is defined. So we have, I don't know, the sinus or cosine curve, for example, or cosine wave. And the disadvantage here that we have a static mesh, and we can't model wave breaking, for example, because we have no coupling. There's just a prescribed surface. And our idea is, or our approach is that we have a united mesh, so a simple mesh, and the interface is somewhere in between the elements of our mesh. So we have a dynamic interface. And the disadvantage here that we have a diffusive interface, so there's no explicit definition where the interface is located. And in this case, to explain this a little bit further, you can see here this little orange section here from the middle, a little bit zoomed out or zoomed in. And as you can see, the surface is dividing the cells into two parts. And one part is filled with water, which is marked here in blue. And if you imagine you have, I don't know, maybe 40% air on the left cell, then the concentration, so to say, is 40% in this case. And to get this information where water and where air is, we solve an additional transport equation. So to get this C value in each cell. And that's the basic idea of our model. And for this, we're using our institute's own solver. It's called Fresco, and it's developed 10 years ago for shape optimization, drag calculation, and also fluid structure interactions, so a lot of engineering applications. For example, you can see here a vessel or a big ship, and you see an LES simulation of the velocity field. And you see, for example, here a big wake region behind the ship, so where a lot of turbulence occurs. And another example would be here another ship that is floating in the water, and you can see some interaction between the ship and the waves. And the goal here was to calculate the forces that are acting at the ship and how the ship behaved in the sea state. And for this, the code was developed originally. And you can also use the code to simulate some more academic stuff, for example, a rising bubble. In this case, we have just a heavier fluid and a lighter fluid, and we have a bubble that is influenced by surface tension, it's rising, and we can analyze its shape, for example. So a little bit more academic and less engineering. And this approach or this solver is based on the final volume method. Most of you might know this method. It's solving the incompressible and Navier-Stokes equations. And for this, we're using a pressure correction scheme. In this case, it's a simple algorithm that we are using. Yes, and just some math or some basic equation that we are solving. First of all, we have the combination of mass, which is basically just a divergence-free velocity field. The second one is the momentum equation. I do not want to go into further details, but just for explanation, we have here a temporal term, we have the convective term. On the right-hand side, we have the pressure, this P effective, that is acting, or that is acting that is coupling the pressure and the velocity. We have some viscous forces, and we have also gravity, and we have the third term on the right hand side, which is the surface tension. So we can also consider surface tension effects, for example. And the next equation, or the third, if you want so, equation is the equation of state. And this is C, the concentration that I mentioned before. We have again a temporal change or temporal derivative. We have a convection term, and what is new, or what is a big difference from our model to models that have been used before, is this right-hand side, where we have some sort of viscosity. So this is a term that manipulates the diffuse, how diffusive our interface is. So how much cells have values between 1 and 0, and not just 1 or 0. So how much mixing do we have, or how big is our interface basically? And we have also some additional equations. So we are solving a turbulence model. In this case, we are using Ran's LAS model, which is basically we have a hybrid model. So we have close to the wall, we are modeling turbulence, and far away from the wall, or a little bit more far away from the wall, we are resolving turbulence. And this model turbulence is based on these two equations for K, which is the turbulent kinetic energy, and omega, which is the dissipation of the turbulent kinetic energy. So we have two more transport equations. I will not go into further details here. And the last equation that we are using is some sort of a distance estimation, because for post-processing and in general also for the modeling, for the turbulence modeling, we need the information of the distance of each point in space to the interface. And for this, we're using a simple Poisson equation that we are solving. And now some basic information about our grids that we are usually using. Our grids are around about 30 million cells big. So we need parallel computing capacities. For this, we are using the HLRN cluster, which is a big research cluster located in Göttingen and Berlin. So the simulations are performed on big servers, so to say. They need some time to calculate. And here on the bottom side, you see a typical mesh. So we have our domain is subdivided into 3 areas. We have a forcing zone at the inlet, where we can generate waves that some, I don't know, maybe linear waves, for example, that start traveling from the left to the right. So within this forcing zone, we are manipulating the equation system basically, and say, okay, we force the equation system to a certain solution, to a solution of a linear wave, for example. Then the linear wave travels from the left to the right. And within the study area in the middle, we are analyzing the data. And on the right-hand side is something like a damping area or a numerical beach that is basically used to damp out the waves and to prevent reflections from the right-hand side of our domain. Yeah, that's basically it. And for post-processing, as I mentioned, we need this distance. So we introduced 2 new coordinates, and this is the surface distance and the phase. And the phase phi is something like the phase state of the wave. So when you have the cosine wave, for example, phase of 0 would be the wave crest. And as you can see here on the right-hand side, there's a little sketch that should explain this a little bit further. So when we have here a green interface, which might be the interface between water and air, and we would like to describe the position of this element of this little red box here, we could describe this point as a function of the global coordinates x1 and x3, so the horizontal and vertical coordinate, in this 2D example here, or we can also explain the coordinates of this point by the distance. This is the orange arrow here, or the orange vector, and the phase phi of the wave. So at each point of the wave, we have a different phase position, so to say. And we can get this phase information from the Hilbert transformation, which basically just Fourier transformation of our surface elevation of the wave. And so we can do this, so we can perform, or we can do this this coordinate transformation. And in the end, the idea is that we have a flow quantity. So for the velocity, for example, an instantaneous quantity on the left-hand side, we can decompose it into a mean value, which is signed by these brackets here, and the turbulence fluctuation. This is called the classical Reynolds decomposition. And the idea is that we can use our coordinates to do a triple decomposition. So in this case, we can decompose our mean value, which is a function of phi and theta, into another mean value that is basically an average along all phases of the wave, which is u bar, and a deviation from this average from before. So we have an average that is the phase average, and we have the wave-coherent quantity and this turbulence fluctuation. And we can decompose every quantity that we have in our simulation into these three parts. And in this case, the averaging process is a big, it takes a lot of data. And so we have a lot of 3D-dimensional flow data, and the post-processing is necessary to get these phase averages, for example. And now we come to some results. Some basics. First of all, some basics. A wave has always a certain amplitude. In this case, the amplitude is called A, and the wavelength lambda. And this P in this case denotes that it's the peak frequency component of an analyzed spectrum. So usually we have not just a pure cosine wave because of this coupling between two phases. We have a whole spectrum of frequency components, but usually the spectrum is very narrow banded. So we have one peak frequency that is dominating, so to say. And we define our parameters by this frequency or by this amplitude and frequency of this peak value. And furthermore, we can define two more classic parameters. One is the one is the wave number k, and the other one is the phase velocity, which is basically just the propagating speed of the wave. And another thing that is pretty important, we have, as I said before, this talk is for wind forcing, so we have some inlet conditions at our boundary, at our inlet, and we define a log law of our wind profile, and this log law is defined by this equation here, and as you can see, this tiny u star here is the friction velocity, and it is basically the slope of our log law. And using this u star, we can define two really important parameters in this case. And one is the wave slope. It's basically the product of the amplitude and the wave number. And the second one is the wave h. And this is two definitions, but the most common definition is that the wave h is this phase velocity, so the speed of the wave, divided by this friction velocity, which basically has something to do with the wind forcing. And older waves, or young waves in this case, when the wave h is very, very, very small, then we have a very strong wind forcing and less very slow wave, so to say. In this case, most of the momentum and energy is transferred from the wind to the sea. And for old waves, it's the other way around. So for old waves, in the extreme example that we have no wind, the waves or the swell is pushing the wind and is transferring momentum from the sea to the wind, to the air. So the wave h is a pretty important parameter in this case. And now we have a look at the instantaneous velocity, and most of all examples that I will show now is for young wave, and it's a very steep wave. So we have very strong wind forcing in this case. And all the experimental data are coming from two different papers of more or less same research group, so from Mark, basically, and Jeff. And as you can see here, we see the instantaneous velocity is normalized here by this U10. U10 means the velocity 10 meters above the surface. And this is just used for normalization and for comparison. And you can see here, the left-hand side is always our simulation, the right-hand side is the actual measurements. And you see here's a lot of air separation behind the wave crest. So the wave is going from the left to the right, and the wind is going the same direction, but is way faster than the wave. So we have here also the simulation, some air separation events happening, and it's very likely to occur. And
experimental data is from the field, right? With a real raw wave spectrum and on peak wave, right?
Sorry, can you repeat?
In the data, the observations is field data.
It's
wave spectrum.
This is data from a wind wave tank, but it's still pretty narrow banded. So they have multiple frequencies, yes, but there's one main frequency, one peak frequency still.
And the spectrum and the model and the observations the same.
Yeah, it should be more or less, or it's very comparable, so it's quite similar spectrum in this case, yes. But the I have to admit that the scales here are quite different. So here we look at from 0 to 2, it's not normalized horizontal direction. Here we look from 0 to 6, so it's a bigger frame, a bigger picture on the left hand side. But we have some better comparison than on the next slides, I think.
Yeah, so this is the tank.
The tank is, in this case, the wave we're talking about is about 1.5 meter length, and the depth is, I think, 70 centimeters, so more or less one wavelength. So
the wavelength is the same as the water depth.
Yeah, the water depth is a little bit, yeah, but in the same dimension or same order of magnitude, yes.
Water wave.
Well, but it's also not fully shallow water, I think. In the model, it's the same. In the model, we have also this the water depth, and the water depth is the same like in the wind wave tank. But this is, as I said, just an instantaneous velocity field, so the wave could look different in another moment, or the velocity field could also look different. And another instantaneous or interesting quantity that we can look at is the vorticity. In this case, the vorticity is defined by the horizontal velocity of the partial derivative of the horizontal velocity in the vertical direction minus the vertical velocity or the partial derivative of the vertical velocity in the horizontal direction. And here you can see the picture or the field of the vorticity. It's also again normalized somehow, and you may identify here some very small negative islands here behind the wave crest, and these islands can also indicate air separation that is happening. So the model, this is for my model. This is simulation data.
Not just the perpendicular point dimension.
What is about the y dimension?
Yeah, you have an X and Z. You also have a Y dimension of the tank.
Yes, exactly. In the model, it's pretty small. In this case, it's a model. It's about half a wavelength, and in the reality, I think it's about twice the wavelength, for example. So the model
fully developed turbulence then.
I think so, yes, but the most crucial point is the length of the tank. So that in our model, the real tank is way longer than our model, and that the question of fully developed turbulence, we can see this on the next slides, is the more crucial when with regards to the length of the tank, of the numerical tank. So the numerical tank is not, or can, the length is way smaller than in the reality. So, but the y direction that you mentioned is not that important for this turbulence or this fully developed turbulence.
Other y dimensions.
Yes, we did. And the problem is that
no difference.
Not a big difference, no. And now we can have a look at some mean quantities. In this case, we look at the mean velocity field. So as you remember, this mean velocity is indicated by these brackets here. There's a function of phi and zeta. And here again, we see simulation and experimental results. So simulation is again on the left. and experimental results is again on the right. And on this, at least on this slide, they look fairly similar for this particular wave case. And I don't know if you can see it on the, no, you cannot, okay, but you can also see if you look closely, and it has a better background, so to say. You can see here the slight orbital velocity of the wave, but because of the young wave age, it's barely visible because the wind is way faster than the orbital velocity in this case. And another, now we can have a look at the wave-coherent velocity. As we remember, this wave-coherent velocity is also a function of phi zeta, but is basically the field of the slide before, minus a vertical profile, so minus average along all phases. So basically the one from the slide before, minus some profile that is averaged along all phases, and this is resulting into these wave coherent velocities, which are basically describing the difference between this vertical profile and the velocity field as a function of the phase. And in this case, it's also again normalized here, and you can see it's pretty similar. The values of the simulation are a little higher in this case, and you can also see now, hopefully, this is the orbital motion here. If we look here closer, okay, the color scaling is quite bad in this case, but you could also be able to see these orbital motions, and the general pattern is pretty nicely reproduced by the simulation. And another quantity we can look at are the Reynolds stresses. In this case, we look at the horizontal Reynolds stress, which is basically defined by an average of this horizontal turbulence fluctuation, of the product of the horizontal fluctuation squared, so to say. And here you can clearly see that the simulation is lacking a little turbulence. And this is probably due to that we have not yet a fully developed turbulence case in this case. So we might have to improve with regards to the Reynolds stresses. And
also function of your parameter in the model.
What exactly should be a function of our model?
For the turbulence.
Yes, this is depending on our mesh resolution, right? But the idea of this hybrid model is that our Reynolds stresses are a function, or are basically separated into a model part and a resolved part. So some of our Reynolds, or some of our turbulence is resolved directly by our mesh, and some turbulence is modeled, and for this we're using this k omega equation stuff. But as you can see, we might have to improve, for example, our boundary conditions to faster get to a fully developed turbulence state, so to say. This is a full turbulence as we are seeing here. So this is both parts of the left-hand side. So we see model plus our resolved turbulence, but it's still not that big like in the experiment in this case. And we also can look at another component. In this case, is the vertical Reynolds stress. So the product of the vertical velocity fluctuation. And as you can see here, we match the overall Reynolds stresses a little bit better, but we still lack a little turbulence here at the windward side of the wave. So the wind is coming from left to right, and here we are still lacking some turbulence in this case. In this case, exactly. Yeah. Our boundary here on the left-hand side is a little thicker, yes. And here, our third component would be the one free direction, so the product of our horizontal turbulence fluctuation and our vertical fluctuation. And here it looks like we are doing pretty good job, but there's still missing turbulence very close to the surface, so we're not reaching these dark blue areas here from the experiment. And also the red areas, so the positive region on the right-hand side of the wave crest is also a little smaller than in the experiment. But I think the widths are still pretty nice in this case. And if we look at the vertical profiles, so we can also not look at these fields that are a function of phi and theta, but just at these profiles that are an average along all phases. Here, the first one is our vertical velocity profile. So blue in this case our simulation, red is the measurement. And here we are, we missed a little. We don't exactly hit the velocity profile of the measurement. In this case here, what we see here is something like these wave-coherent velocities that I showed before. And you can also calculate the stress from two components of this wave-coherent velocity. And this is pretty nicely reproduced by the simulation here. And here we see on the left side these three components of the Reynolds stress that I showed before. And the main difference is this horizontal component. So the second one from the right, where we are missing some turbulence, but the basic shape, for example, is reproduced pretty well, I think. But yes, we are missing some turbulence right now. Yeah, as I said, the horizontal Reynolds stresses are underestimated right now. But we can also look at pressure drag. And the one advantage of our simulation is that the pressure calculation is part of the simulation process. So we get the pressure as a flow quantity as output. And for the measurements, they have to reconstruct these pressures. So the right-hand side is again measurements, but they had to reconstruct these pressure fields from the velocity field that they had. And as you can see, the pressure patterns or distribution are quite similar. Also, the scales are pretty similar. And here on the bottom line, you see the surface pressure along the surface of the wave. Here, and you see the red line is the pressure, and the black line is the basic generic shape of the wave, so that you can imagine where the high pressure occurs and where the low one is. And the idea is that you can use these pressure fields to calculate the form drag of the wave. And this is quite interesting or important to estimate the wave growth, for example, or how much energy goes into wave growth, because most of the wave growth comes from the drag of the wave, basically. And this drag can be estimated from this pressure field here, P, and eta in this case is the surface elevation. So this is the horizontal derivative of the surface elevation. And this bar here above means that we average along, this refers to the phase averaging, and this means that we average along the whole wave or the whole phase average wave, so to say. And then we can get this tau d, which is basically the drag. And during the post-processing, we got a drag or a normalized drag. This drag is then often normalized by this U star from before that I introduced. And in this case, it's 0.69 for this certain wave scenario. And when we look at literature, this is a picture from a paper from Wu from last year, I think, and they compared a lot of, hopefully you can see something, they compared a lot of different studies and their results of the drag coefficient. This is just slightly differently normalized here, but the vertical axis is the drag, and the horizontal axis is the wave slope of the wave. So how steep is my wave? And this orange cross here is our value, and it's fitting pretty nicely into this literature data in this case. From the tank or from the model also? This is from our model, our numerical tank, so to say. There the value was also somewhere, it should be, somewhere in between, somewhere here a little bit below, but we hit it pretty nicely. I'm not sure which of the dots is from the experiment that I showed, but as you see, there's a pretty, there's a little bit spread in the data. So but I think we are hitting it quite well in this case. Yes, and in the end, to some future directions, basically our main issue that we have not enough turbulence, so to say, to match the experimental data perfectly. This could be resolved by, for example, improving the boundary conditions with synthetic turbulence, for example, so that we get faster to this fully developed turbulence. Or we have to increase the length of our wave tank, for example. This would mean a lot of more computational effort in this case. So our current idea is to improve our boundary conditions. In general, the drag and most of the mean quantities agree quite well with at least this experimental data. And in general, our model seems to be quite promising method because we can also look at more complex things that are quite hard to reproduce in the experiment. For example, wave breaking, or can also include, you can also consider capillary effects, so influence of surface tension, for example, and stuff like this. And for a little outlook, in the future or right now, we are evaluating a wider parameter space. So not only one wave or a second wave or third wave, but maybe 10 or 20 waves that have different wave ages, different slopes, and different Reynolds numbers. And we would also like to look at breaking events, for example, and what's the influence of these breaking events on wave flow, for example, or current generation. And in the future, the main goal is to provide some kind of parameterization for Lars and the ocean modeling, and to bridge finally with the ocean modeling. But this is still a feature right now. Yes, thank you for your attention. And feel free to ask any questions.
Okay, for this talk, is there also more from the audience? Are there questions?
Lars has raised his hand.
Yeah. Lars, do you want to ask a question?
Yes, hi. Thanks, Malte, for the nice talk. I have basically two questions. One question is, can you go to the slide where you had the pressure or the pressure reconstruction? So,
yeah.
So do you know why this is basically directly in the trough? So I would expect that it's just the wind on the windward side pushing against the wave, right? But why is it so directly in the trough? Is that obvious?
Not 100% sure. One thing I might have to mention is that the representation of the wave field might be a little bit misleading, because we are not comparing that, the wave flow